Sneha, I am here for explaining the topic of inorganic chemistry, chemistry of noble gases. Or we can say that today we will study about group 18 elements. So group 18 elements mainly comprises helium, neon, argon, krypton, xenon, radon, in which this radon is radioactive in nature. If we talk about the general electronic configuration of this group, that is Ns2 and P6, or we can say that they possess fully filled valence shells. Due to which is the reason why they are being called as noble gases. Now we will study why these group 18 elements are more appropriate to be called as noble gases rather than inert gases. So if we study the literal meaning of the word inert, it means that these gases do not react with any element which exists on Earth, which is not true, as observed by Niels Bartlett. Niels Bartlett was a British-born Canadian chemist who was working on PTF6 for a long time. Here, PTF6 is a red crystalline solid which he took under consideration. He observed that PTF6 is exposed to when PTF6 is exposed to molecular oxygen, then a yellow ionic solid of O2 positive PTF6 whole negative, this compound is formed. So the reaction is such that when oxygen reacts with PTF6, it gives out O2 positive PTF6 whole negative. Here this PTF6 is orangish color, reddish orange color, and the resultant compound formed, it is of yellow crystalline nature. Bartlett also observed that oxygen molecule and xenon have quite comparable first ionization energies, and therefore he predicted the reaction between xenon and platinum fluoride to form xenon positive and PTF6 negative. That is, when xenon reacts with PTF6 compound, it gives a new compound which is again of yellow color, Hc positive PTF6 whole negative. This formation of compound of xenon proves that noble gases, as group 18 members, are not completely inert, as it formed compound with PTF6. Also later on, other compounds were also formed of xenon such as XeF6, XeOF4, XeO2F2, XeO3 and XeO4 also. So now let's get started with compounds of xenon. So now we will study about compounds of xenon. First of all, we will start with XeF2. Its preparation is if xenon reacts with fluorine in presence of nickel at 400 degrees Celsius, XeF2 will be formed as product. Or it can also be formed by the reaction of xenon with O2F2 at minus 80 degrees Celsius temperature. One more way of the formation of XeF2 is the reaction of Xe plus fluorine under the influence of electric discharge. So now we will study about the type of bonding that takes place in this compound. So if we talk about the outer electronic configuration of xenon, that is 5s2 5p6. Now we can show it diagrammatically as this. This is the isolated xenon atom in which all the electrons are in paired form. As we know that fifth shell also comprises of d orbital, which can be used for bonding when there are two fluorine atoms available for the same. So what happens is this: there are 2 electrons in 5s2. So here one electron is excited from 5p orbital to 5d orbital for the incoming 2 fluorine atoms. So one fluorine atom will give electron which will go to the 5p orbital like this, and one electron from another fluorine atom will go in the 5d orbital in this way. So in this type of bonding, it is clearly seen that here 1s3p and 1d orbital is used for hybridization. So we can call this type of hybridization as sp3d hybridization. If we talk about the shape, of this molecule. So let's observe the upper diagram again. As we can see clearly here that we have 3 lone pairs out there and 2 bonds, so we can make the shape of the molecule like this. We can say that HCF2 possess linear geometry. Similarly, in HCF6, if we draw the diagrams, so in HCF6 molecule, we want 6 vacant places where these 6 fluorine atoms can reside and take participation in bonding with xenon atom. So as we can see here, if 3 electrons of 5p orbital are excited to the empty 5d orbital, then we will be able to make space for all these 6 fluorine atoms. So let's do it. Now, one fluorine atom can make a sigma bond at this spot by giving one electron. One electron can be accepted by another fluorine atom here, and in the same way, in all the vacant places, fluorine atoms make their sigma bond, and thus our HCF6 molecule is obtained. So if we talk about its chemical reactions, when HCF6 undergoes hydrolysis, or we can say that when it reacts with water, it gives xenon trioxide, that is XgO3 plus HF. This is a powerful explosive. If we talk about the hybridization of HCF6 molecule, then here it is clearly seen that 1s orbital, 3p orbitals and 3d orbitals are occupied in this hybridization. So we can name it as sp3d3 hybridization. So talking about hybridization, it is sp3d3. If we talk about the shape of the molecule, then as we can clearly see here that there is one lone pair and 6 bond pairs, so its shape will be somewhat like distorted pentagonal bipyramidal. And the reason behind the distortion is the presence of lone pair. So here is a diagram of HCF6 molecule, in which we can clearly see that due to the presence of lone pair, this octahedral arrangement becomes slightly distorted, or we can say that distortion is observed in the compound due to the presence of lone pair. Now let's study about the molecule XeO2F2. Similarly, in this also, firstly we will diagrammatically represent the valence orbitals of the xenon atom, which is 5s, which is 2 electrons with opposite spin, 5p, which is 6 electrons. So this is the compact structure of xenon atom, in which there is no space for further bonding of other atoms around the xenon atom. Now, as we know that xenon atom possess 5d orbital also. Now, there are 2 oxygen atoms and 2 fluorine atoms that are to be bonded with this xenon atom. And 1 oxygen atom needs, here we know that oxygen atom makes 2 bonds, that is 1 sigma bond, 2 kinds of bond, 1 sigma bond and second is pi bond. So here, as we can see, that we have to unpair all the 3 electrons in the 5p orbital. After this, the picture of the molecular orbitals will be like this of the xenon atom. Now, 1 oxygen atom comes in the vicinity of the xenon atom and occupies the place here, making a sigma bond, and the another place occupying for making pi bond. Similarly, the another oxygen atom did this in the same manner, forming sigma bond and pi bond respectively, and the remaining 2 fluorine atoms, one fluorine atom gave its 1 electron in this orbital. Similarly, the second fluorine atom gets accommodated in this orbital. In this way, we get the XeO2F2 molecule. Here, when talking about hybridization, shape and structure. So when we talk about hybridization, it is clearly seen in the upper diagram that 1 s orbital, 3 p orbital and 3 d orbital are used in the bonding and in the formation of this XeO2F2 molecule. So the hybridization of this XeO2F2 molecule is sp3d3. So the shape of the molecule is very much similar to that of the previous one that we have studied, that is distorted trigonal bipyramidal. When we talk about the structure of this molecule, we have very well explained about the structure of XeO2F2 molecule, that how it occupies this hybridization and the shape. An interesting fact about the noble gases is that they form clathrates. Clathrates are the cage-like compounds in whose cavities we can store certain organic and inorganic certain organic and inorganic compounds by trapping them in the cavities of these compounds. So this is the main application of noble gases. That these are used to store certain compounds which are not possible to be stored in any other way. They can be trapped in the cavities of these clathrates and used later on whenever required. So this is the important application of noble gases. Furthermore, still we don't know that much about noble gases, but yeah. Also, these noble gases are used for making bulbs. For example, neon bulbs, argon bulbs. So these are the important applications of noble gases along with their importance in the laboratory. Thank you. That's all for today's video.